I'm happy to introduce our keynote speaker, Christopher Hall, who is the Senior Flow Cytometry Technical Specialist at the Flow Cytometry Facility at Barberham Institute. He's going to take us on some adventures in full spectrum flow cytometry. So Christopher, if you'd like to share your slides.
That's no problem. I should point out that's our team before we start.
Looks good.
Not at all photoshopped. Okay, let me just move my little. Okay, hello everyone. It's a pleasure to be talking to you today. I'm going to be talking about spectral mixing mainly in full spectrum flow cytometry. And I'm Christopher Hall. I am the Senior Flow Cytometry Technical Specialist at the Barberham Institute in the UK and ISAC SRL Emerging Leader. So first of all, we should really point out that none of the machines on the market are actually full spectrum flow cytometers. I won't class anything as full spectrum until it's maybe 1 nanometer per detector. They're just flow cytometers with even more detectors that can analyze an even greater range of the spectrum. So the Bigfoot, I think ours is 54 detectors. The Aurora has 64. I believe the ID 7000 from Sony has 120. But still, they're not going anywhere near full spectrum. But that's beside the point. I was just thinking about this last night and it annoyed me. If you want to know a little bit more about full spectrum, I was talking about yesterday. I won't talk very much about the concept behind it, apart from this very important starting point. So on the left, just let me get my pen out. So on the left, we have what we classify as a traditional flow cytometer. We have 2 fluorophores, and these are the emission of the fluorophores, the blue and the red, and we have 2 detectors, and we try and match the detectors to the peak emission of the fluorophore. And this is how a traditional flow cytometer works. And this purple area here is the compensation. This is the spillover, and this is why we have to use compensation. On a full spectrum machine, we have lots of detectors, and we use all of the detectors to analyze every single fluorophore. So we're not looking at the peak channel, we're looking at the entire spectral profile. And to that, we have to apply something called a mixing, which is a way of separating out the signals by using the controls to estimate the amount of signal from each fluorophore. So here it is in a practical example. So on the left, we have a spectral profile of an experiment I did last week for this presentation. It's 10 colors on lymphocytes. And we can see that the spectrum on the left is very complex. There's lots of different fluorescent quantities in every single detector. And in spectral flow cytometry, we do unmixing. So we have on the right some pure spectra of, say, CD4 APC, CD3 PE, and I don't know, CD14 Percy-P. And from these spectra, we have to work out the relative proportion of these spectra in this mixed spectra. And that is conceptually difficult to grasp, but mathematically not particularly difficult, and something that's been happening for a long time. And so what I'm going to talk about today is unmixing and different ways of doing it in order to display the data in various ways or to answer more questions from the data. So if you remember, you've got your flow cytometer is something called an overdetermined system. It has more detectors than parameters. So you've got on this Aurora 64 detectors, and we have 10 fluorescent parameters. And so we have loads of data that previously, before unmixing, we just threw away. But we can actually use this data to answer different questions. And so here is a nice example of 2 spectra. So it was mentioned yesterday that the fluorophores are quite often badly named. So these spectra look almost identical, to me at least. But on the left, we have Alexa Flow 700, and on the right, we have Super Bright 702. And yes, the Super Bright 702 fluoresces, the peak fluorescence is in the violet channel, and the Alexa Flow 700 peak fluorescence is in the red channel. But overall, the spectrum are incredibly similar. However, we can very easily unmix them. So we get a very nice separation. And so how do we do this? So to do this, we have to do a little bit of maths, but we're going to start with compensation. So I often find that people kind of pass off compensation as something you do and it's very, very simple. And it is not particularly complicated. But you've got it conceptually, we should understand how it works so that we can move on to unmixing. So the next few slides are going to be talking about how compensation is actually applied to your data. So with compensation, we have controls. So we have 4 controls here, understand FTSE, P, and APC, and we have the median fluorescence intensity of each of those controls. And what we want to do is create something called a spillover table, a spillover matrix. And this shows us how much each flow spills into the other channels. And to do that, the formula is quite simple. We take the fluorescence in the target channel, so the FTSE and the FTSE channel, and divide it by the fluorescence in the spillover channel, so how much FTSE is in the PE channel. And then we do a 1 over that number to get a percentage. So if we do this by hand, it's not particularly difficult. So we have 20 MFI of FTSE minus 2, so that's 18, divided by 5, which is 3.5-ish, 3.6. And then we do 1 over 3.6, and we get this number on the left, 0.28 or 28%, as you'd see on the machine. And we continue to do this. So for the next one, we have 20 minus 2, which is 18, divided by 1, which is 18. And 1 over 18 is 0.06, or people would say 6%. And we just keep doing this over and over again until we fill up the whole matrix. Like so. I should point out that maybe with the spillover channel, we could have done the 5 minus 1 as well, but just to make this slide a little bit easier, I didn't do that. And so we have this square matrix where we have our channels and we have the amount the flow spills into the other channels. Very simple. But then how do we apply this to the actual data? And so this is the bit that got me for a little while as well. So we can conceptually think it's okay. There's 28% of the FTSE goes into the P channel. So maybe we minus 28% from this, or 28% of 2 from that. Then we do the same for the APC, but then do we do it back in the other direction? And so what you need to understand here is if you did this at, so I should apologize if you did this at school, and this is very obvious to you, I apologize, but I don't remember doing matrix multiplication at school, or because it was so long ago, I can't remember it. So we have to do something called matrix multiplication. But before we do this, we have to invert the matrix. So for compensation, we actually have 2 matrices. We have on the left, the one we just calculated, this is called the spillover matrix. And on the right, we have something called the compensation matrix. And it's this compensation matrix that we actually apply to our data. So to make a compensation matrix, we have to invert the spillover matrix. So this on the right is an inverted version of the chart on the left. And to do this, it's not hugely difficult, but it's much faster on a computer than it is by hand. Basically, what you do is you make an empty matrix on the right. So we have the 1s across the diagonal and everything else is 0. And we do row-wise operations. So what we do is we do a calculation on the left-hand side to make this P 0 and this APC 0. But we do the same calculation on the left. And so what ends up happening is you end up on the left with 1, 0, 0, 0, 1, 0, etc. And on the right, we have the inverted matrix. And so it's quite trivial with compensation, because with compensation, we've already started with the 1s across the diagonal. And so actually all we're doing is we're adding basically negatives here. But you should be aware that this is not always true when you invert the matrix, and it just happens to be the truth when we are doing flow cytometry compensation. And so obviously you can do this by hand, but if you Google, there's lots of nice videos of people doing it, but it takes a long time. In reality, we have computers. In Excel, you can use this matrix inverse command. In MATLAB, inv-x, x being the matrix. And in R, which I use, you can use solve-x. And what it does is it produces this inverted matrix. So you see we have this new matrix that's inverted. This is the compensation matrix. And so now we apply this compensation matrix to our file, to our events. So here we've got 3 events, 1, 2, and 3, 1, 2, and 3. And we have the median, we have the fluorescence intensities of the different channels. And so we have to apply this compensation matrix to these events. And to do this, we need to use matrix multiplication. So conceptually, when you look at the compensation matrix or the spillover matrix, anything in the columns, this is how much the FTSE is spilling into the other channels. Oh, sorry, how much the PE is spilling into the FTSE and how much the APC is spilling into the FTSE. And on the rows, this is how much the FTSE is spilling into the PE and how much the FTSE is spilling into the APC. And we can see it is 0% there. So with matrix multiplication, you multiply rows by columns. And this is really important for understanding what goes wrong with unmixing in a second. So if we do it for this number 2, so we're going to apply the compensation matrix to number 2, we do the following. We go across in this direction and in this direction. So we take 1.01 times it by 2 plus minus 0.04 times 22 plus minus 0.05 times 2. And that gives us a final answer of 104. And so our true fluorescence after compensation is 1.04. And for the 22, we do the same. We have minus 0.28 times by 2, 1.02 times 22. So you see the pattern we're doing, and minus 0.4. And it gives an answer of 21.84. So we do this matrix multiplication to work out the true fluorescence of every single value. And then we end up with something like this, with the fluorescences that we see on the machine. And this is compensation. This is removing the spillover. And in this matrix, we can see here, we can see some classic artifacts of compensation. We have a minus number here because we've removed more fluorescence than there was actually in the detector, which is why we have to update a transformation later on. And over here, we actually end up with more fluorescence. So if we go backwards, we end up with 22, and now we've got 22.14. So our fluorescence has increased because of compensation, which doesn't make sense and physically is certainly not true. But when we inverted the matrix, we ended up with 1.01. So we ended up with more fluorescence after the compensation. So it's good to understand these basics of compensation, because we need to understand the difference between compensation and unmixing, because unmixing is a much more powerful tool with many more variables and many more ways of changing the data to however you want it to look, basically. So let's try and apply this to unmixing. So we've got the same formula here. We have 4 controls. We have the unstained, the FTSE, the PE, and the APC. We have 6 detectors. And we have the fluorescences of the controls. And so if we wanted, we could take the peak channels, for example, and do the same calculation. We have the 1 over the positive divided by the other negatives, and we get this beautiful spillover matrix. But this is not how it works. And it doesn't work like this, because how do you choose which detectors represent each control? So imagine doing a multiplication like we did before. So if we had the FTSE times the 20, because we're going to choose that, the PE, which one of these do you choose for the PE? Say you choose that one. For the APC, you choose this one. But then suddenly, there's nothing else. You can't actually multiply this table together. So you can't do unmixing the same way as you do compensation. And so, maybe there's a slide telling you this. We can't multiply 6 columns by 3. It's not possible. So we do unmixing, and generally they call it weighted ordinary least squared unmixing. And to invert this matrix, we use something called Moore-Penrose generalized inverse, which I can't go into the maths of. And then we apply this to our data, which I'll talk about in a couple of slides' time. But this, I think, is the last slide of maths for now. But generally, this is what you'll often see, is that people tell you there is no perfect answer to the unmixing. So with compensation, you've got 3 rows and 3 columns. So there's mathematicians say there are the same number of formulas as there are parameters. So you always get this perfect correlation. So we have this perfect line here. This is just a graphical representation of nothing. But what I'm trying to show here is that if this is compensation, this is the regression. So it's perfect because there are no alternative answers. But with unmixing, we have variation. Because we have more detectors than we have fluorescent parameters, there are multiple answers to this question. And we can adjust where this, so this is the regression I've put here, but we can adjust this depending on many factors, including which algorithms we use and what weighting we use. And that's what I'll talk about in the second half of this talk. Let's escape from maths for a second, just to let everyone calm down a little bit. Let's talk about making spectral plots. So in the presentations I do, or in my lab book, I have lots of spectral plots because it's something we're very interested in at the moment. The problem is that the vendors lock their spectral plots to their own files, which is fair enough. It's been done all through history. So there's no way of comparing ID 7000 data to Aurora data, or to Aurora data to Bigfoot data, or Bigfoot data to SP 6800 data. Because we need a way to visualize these spectral plots outside of the software. And so, as far as I'm aware, only FCS Express will show these plots. But FCS Express here, it's not the best plot in the world because we have no kind of graduations on the x-axis. So we don't know which detectors are which lasers which. And I'm happy to be proven wrong. If anyone knows any other software that will do it, and we'll actually talk about other R packages that will help you with this later on. But for now, just for my own presentations, I produced something called Flow Spectrum. So here's the address, github.com/Flow-Spectrum. And what it does is it understands what ID 7000 files, Bigfoot files, and the Aurora files look like, and it will automatically put the spectra. And so this gives us the opportunity to consistently produce visualizations, but also it allows us to compare across machines, which is very useful. We found it actually really very useful. And this can also be done off the analysis machine, so you don't have to waste time. It's just a wrapper for ggplot too, but it works quite well. It doesn't work with the SP 6800 because, as far as I can tell, their spectral files are proprietary, and I don't know how to read them. We also have these normalized plots. So this is PerCP 710. This is PerCP 710 as well. And it just gives us where the peak channels are. We can see PerCP. It's not surprised. Most of the PerCP colors have these multiple peaks. But having multiple peaks isn't a bad thing in unmixing. Okay, so let's move away from the full spectrum machines and move to the lesser full spectrum machines, which be even less because they're not actually full spectrum machines. I'm getting myself confused. Let's unmix on the Fortessa. So it was actually mentioned yesterday, and you can readily unmix on a Fortessa. So the mixing algorithms need an overdetermined system. An overdetermined system is a system with more detectors than fluorophores. So if I have got a 10-color panel here, and I've got an 18-color Fortessa, so it's overdetermined. I've got more parameters. So theoretically, I can do some unmixing, and it's 100% correct. So on the left, we have the compensated data. On the right, we have the unmixed data. The unmixing was done in R using LSFit, and it all obviously looks the same. I think, yes, there's a slight transformation difference here, but the zeros there and the zeros here, so it doesn't make a huge amount of difference. But we can see that I can see my CD3 population. It's not as well separated, I'll give you that, but that's not a surprise because there's a lot less spare detectors. With the CD8 and CD4, on the left, it looks fantastic. On the right, we see it worked, technically. I mean, there's slight percentage differences here, which isn't ideal. But the unmixed, if I worked a bit harder, I could probably get this work perfectly. We can see this double negative here. This is very classic of an unmixing error. If you ever see this, or you see some sort of cross, that's very classical of an unmixing error. And we can obviously see that this hasn't unmixed very well in the CD8. But conceptually, there is nothing stopping you from unmixing any machine as long as you've got spare detectors. And this is a good thing, because what I'll talk about very soon is different ways of displaying the data and different ways of changing the unmixing algorithm. And we can apply this to our normal machines. And we have one more slide. So we've got the CD16 and CD14. we can see almost identical percentages, which is fantastic on the 14 and 16, but I do lose in mixing my intermediate population, which shows very nicely here. But again, not a surprise because we've got less data density. I was mentioned yesterday about autofluorescence subtraction on the Fetessa. And I can tell you that I cannot subtract the autofluorescence on a Fetessa. Well, not with a decent number of parameters. However, I can subtract the autofluorescence from the ZE5. So the ZE5 from Biorad has 27 fluorescent parameters. So a 10 color panel with 27 fluorescent parameters, we have multiple free parameters. And we can actually do some very nice mixing on a ZE5 with a reasonable sized panel. And obviously, if you were to push the ZE5 to 20 colors, then you're not going to be able to remove the autofluorescence. And because there's a lot fewer parameters, you can remove the autofluorescence as long as you keep these type of parameters free. But it's infinitely possible. And so it was mentioned yesterday by Alexis that the Aurora has 64 detectors. And so you can have much more data. So the fluorescence subtraction works much better on that compared to the Fetessa or another machine. That's true. But the Symphony has 30 plus, nearly 40 detectors. The ZE5 has 27. I can't remember how much some of the cytoplexes do. But there's a lot of machines with a fair number of detectors which you can use linear unmixing for. And of course, if you then go to the Sony ID7000 with 120 detectors, there's all sorts of magic you can probably do. But sadly, we don't have one. Okay, let's move on. Let's go back to a little bit of maths. I'm lying, it's not actually maths, but let's conceptualize what we're doing. So there are multiple algorithms we can use. And there are multiple ways to use each algorithm. And they're quite easy to change, not technically difficult to change. They're impossible to change, obviously, in the vendor software because they've worked out the best way to mix their data. But just like titrating your antibodies, just because it's fantastic for them doesn't necessarily mean it's fantastic for you. And maybe you can improve your data resolution or the quality of the data outputted by changing your algorithm. So let's just go through this top line here. So the algorithm. So if you ask any of the vendors, they say it's a weighted ordinary least squared regression. And they never say what the weight is. And by the way, if someone knows what it is, I'd be happy to be told it. But I don't personally know what it is. So let's talk about some of these words just to get everyone on the same page. The regression is the line. So the regression is just fitting the line to the data. Okay, that's what regression means. Weighted means that you tell the algorithm some of the detectors are more important than the others. So say you are looking at FITSI CD3, just conceptually. You can say that all the detectors that are brightest for FITSI are the most important, and we should fit the algorithm tighter to those ones. Or say that some of the detectors are more accurate than others. They have less variation, perhaps. Then we can say those are more important and we should fit the data closer to those to try and make the data neater and tighter and more reproducible. So on this chart on the bottom right here, this one down here, what I mean by this is say you decide that these ones are much more important than the rest. You can then tell the machine that those are more important and we can change the regression. You could say that these ones appear terrible. And so the machine might go crazy into a regression like that, which would be obviously a disaster for this particular made up data. But by changing the weighting, you change the appearance of the data. And it really opens up some interesting prospects about how you can troubleshoot problems with data. So I haven't tried this, but I was thinking about this the other day. But imagine if you had a faulty detector, you'd run a huge experiment, cost a fortune, and one of the detectors you hadn't noticed was faulty, or one of the lasers was drifting a bit and you started to lose a bit of resolution. You could weight the regression, you could weight the algorithm to either make those ones more important, to remove the variation or to hide the variation perhaps, or to say that these are less important and save the rest. And so it actually opens up some possibilities of saving your data. Ordinary, least. So ordinary, I actually don't know what ordinary means, but the least bit is because you're trying to minimize the variation. So the variation between your regression is the sum of all of the differences between the line and your data. So you are trying to make this variation as small as possible. This is what you're trying to do, trying to make these red lines as small as possible. And that's how you fit the line. And this is the take-home message for anyone who has to do any training for this. This is my favorite bit of this. Why is it called squared? It's called squared because squared numbers are always positive. So if you do this, if you try and fit this, every single time this might be +2, this is -1, this is +1, this is -5, and you end up cancelling each other out, and it makes it very hard to calculate the line. But if every number was squared, so 5 squared equals 25, -5 squared, which is the same in the opposite direction, is also 25. So by squaring all the numbers, it makes it easier, or makes it possible to calculate the best fit. And that's the fact that we tell people when we're training. Okay, yeah, we'll talk about the weights in a second. So I can't go any further without mentioning this paper, published in 2013 by David Gerald and Bartek. And this goes, they were using some of the beta machines, I think, from Paul Robinson's lab, and some computational data to try different mixing algorithms back in 2013. And this is figure 5 from their paper, from Cytometry Part A. And they're unmixing 32 channels, and they choose different algorithms. So here we have an ordinary least squared, so everything above this line. Below this line, we have a non-negative least square, which I'll show you in a second, doesn't work very well. And this one is MAPE based on mixing and Poisson based on mixing lowered. So back in 2013, they were applying different algorithms to try and make the data as representative of the truth as possible. And we can see, we look at the paper, but we can see the data looks subtly different in every respect and choosing different algorithms. And this is the problem. With compensation, there is no alternative answer effectively until you get to the very high dimension stuff. And so the data always looks the same. If I load my data in different softwares, they'll calculate the same compensation. But every software may or may not choose a slightly different algorithm, a slightly different weighting to do the unmixing. And this is important to remember because it makes it harder to reproduce the data across machines, especially if you cross vendors. So what I've done, I'll put this on GitHub at some point very soon. It's a bit messy at the moment, but I'll need to do it up. But there are lots of tools in R already to do this type of work. And so on the left, we've got some of the tools you can use, and I've got code examples for all of them to unmix the data. So we got LM, solve, GinV, QRsolve, LSFit, non-negative least squares, and many more. And so all this work's been done. The mathematicians and the microscopists and the astronomers have been doing this for a long time. If you Google hyperspectral, just the word hyperspectral, which for some reason is set off my OK Google, you will find that you can apply this to flow cytometry data really easily. You just extract it as a spreadsheet or CSV file and apply all these algorithms, and there's lots of them. So as examples here, so I have an unweighted LM, so this is this top one, looks like this, looks pretty terrible to be honest. On the right, we have LSFit, and LSFit, I think these all look the same because they all use this QRsolve algorithm to work, and it looks much better. We have other algorithms, so we have this non-negative least squares, because technically there's no such thing as negative fluorescence, but obviously there is. And we can see that it looks terrible. It looks terrible because everything's binned to 1, basically. So this is like looking at it on a log scale. It doesn't work very well. And this is what the aurora looks like on the right over there we're mixing. So on the right, we've got the aurora. And we can see maybe with this unweighted stuff, there's slight transformation difference as well, which is a bit unfair comparison. But we can see, and in fact, I wouldn't be surprised if it's a very similar algorithm, but they're clearly weighting the algorithm as well. So we need to talk about what a weight is and weighting in general. I should point out that there's a gentleman called Rex Woon who has an R publication page that talks about how to use lots of different linear modeling tools, and it was very useful in working out how to do this. So what is weighting? So as I say, weighting is telling the algorithm which points are more important than others, so that it can fit a better regression. And how do you do this weighting? And there's lots of different ways. This is just a couple of really simple ways to do it, and there's some more complex ways. We can look at the variation of the unstained. So this is the unstained spectra on the right. And what I can do is I can say, look, listen, this detector is fantastic. This one's the next best detector. Oh, that one's not so bad. We'll do that fourth. This one over here is terrible. So let's give that one 64. This one's rubbish, 63. And we can look at the variation, the negative, and say which detector is more accurate, which is producing better data. And then we can weight our algorithm along those lines. We can be even cleverer, and we can look at the stain populations, and we can do a weighting per stain population. And we can say that these are the peak channels, so these are super important. These are the second peak channels for all the detectors, so these are secondary most important. And actually, we should weight it so that these show up most readily and are most clear. We can do it on the QC. So every machine has a QC report every day, or it should do QC every day. And this report tells the machine its own performance. And it can say to itself, listen, these detectors are fantastic, these are terrible. This is what we should be doing. And also we can do some computational tools, which we'll talk about at the end, where you can possibly iterate through different fitting models, different weights, until you find the one that's the best. And we'll talk about that at the very last slide. Okay, so all of this data, apart from the Aurora unmixed, has the same transformation. So the Aurora unmixed here, this is the CD14 versus CD16. I've gated the monocytes just on size parameter, just to make the data a bit cleaner. And here I'm using lsfit, which is one of those commands in R. And what I've done is I've weighted it on my negative variation of my negative events. And we can see we have a nice tight negative now. We can see some separation here. It's not quite as clean as the Aurora, but it's all right. Use lsfit again, and I've done the opposite. So the one in the middle, I'm saying that the most sensitive, or the detectors with the least variation, are the best ones and should be weighted. And on the right, I've said the opposite. I said, listen, I want to be concentrated on the worst detectors because I should remove the terribleness of this data. And we can see we lose a lot of resolution. Our single positive CD14, sorry, is obviously moved to the right a bit. I've lost some separation here. I've gained a TX, this negatives change direction. And it looks a little bit more compact, which is fine. So I'm not going to give you any kind of metrics as to which is the best, because to be honest, it varies depending on the flow flow you're looking at. I'm sure, and there are ways, and we'll talk about a little tool at the end that will do this for you. But what I'm trying to explain here, or trying to show here, is that you can change the output of your experiment completely rationally and completely acceptably by applying slightly different variations of the algorithm. And once you understand how to do this, you can then radically change the algorithm and do really interesting things. So in the old days, in the Caliber, you had 3 or 4 detectors and you could do 4 parameters. And so there was not much leeway in the ways you could analyze the data. You had 4 parameters and that was it. But with these 64, 120 detector machines, we can show we have lots of spare data. And this data is really useful. It's like introns in genomics. They actually do something. And so we should be utilizing this better. And the only way to do that is to understand this in mixing and to be able to do it ourselves, because we haven't at the moment been offered the opportunity to change it in the vendor software. So here I've done what I mentioned before. I said that the CD16 is super important to me. So what I've done is I've told the machine that any of the parameters that were positive for CD16 are super important, and the rest you can fit as you say. And we can certainly see there's a lot more spread in the negative population. But what we can see is we've increased the resolution of the CD16. We've definitely improved the resolution of the intermediate population here, but we've also increased the distance compared to the other ones of the CD16. So we can correct badly acquired data perhaps by doing something like this. And yeah, and this is I can't remember why this one's here. This is LS fit with the negative cells. I think I've already shown you this, but this must just be for comparison to this. So we can see how we've improved the resolution of the CD16, but we've definitely lost some of the negative CD16 as we've got more data spread. And data spread, as anyone who's done spectral mixing knows, is a problem. And this is one of the reasons why I do some autofluorescence subtraction. So the very last slide. So we can talk about computational tools. Yeah, we can talk about computational tools of ways of getting better weighting. So we have something called a residual versus fitted value plot. And on the left, it's unweighted. So this is on, and then the right, it's weighted. And what you want is your residuals to be sitting around this 0 point. And so we can see here from this blue line, unweighted, the residuals are not quite sitting there. And on the right, it's a little bit better, slightly in a different direction. But what you can do is you can iterate through this. And you can say, you can do one and say, well, this is all right, but then the slope is a bit positive, a bit negative. So we do it again, do it again, do it again until it's perfect. So this would be very similar to Autospill. So Carlos Roca at the Liston lab at Bayram and VIB, they built this tool called Autospill, which is fantastic. It automatically gates cells and it does linear compensation on the linear axis, and it's an amazing tool. But one of the best things it does is after it's done the compensation, it looks at all the median intensities of the controls and then very slightly iterates through all the compensation values and changes them to make them perfectly aligned with the negative controls. And so you can do this with unmixing as well. And in fact, there are a few tools out there. So if you go into GitHub, you can search for unmixing and you can find there's some groups already doing this. So there's a fantastic tool by Jacob Farrell called Flow Specs that uses LSFit. And there is a tool called Panel Builder R by Mertek, and I can't quite remember his second name, but the University of Prague. And they use this tool to design bigger and better panels for spectral flow cytometry, to some visualization as well. But also, if you look at it, they have implemented or are implementing multiple unmixing techniques in their tool. And I'm not going to talk about their tool, it's for them to talk about. And you can look in GitHub and see what they're doing. But there is a lot of space in flow cytometry to take advantage of these spare detectors. And so that's the end. Hopefully that was all right. I hope that you will take away that unmixing is not an exact science and that we can change it. And once you understand how to do it, there are many, many interesting things you can do, and not just what I've shown you with these little slight changes. You can radically alter the appearance of your data for the better or for the worse. And I'll put all of this onto GitHub, which will be holy166, github.com, so you can do it yourself. And once you can do it yourself, then you can start playing around and improving the output of your work. Yep, and at Bayram, we also have training courses, Google Bayram Flow Cytometry, and you'll see them all. And Flow Cytometry UK is in a few weeks. Thank you.